Hello everyone, thank you so much for being on the other side of the screen and welcome to this presentation called Vulnerability of Port Areas of Operational Interest, Sensitivity to Climate Change. My name is Alvaro Campos and I'm part of a team formed by colleagues from the Universidad Politécnica de Madrid, Spain, from the University of Castilla-La Mancha, Spain, and from Puertos del Estado, which is the Spanish public organism in charge of managing state-owned ports. Okay, so first of all, in order to settle down the topic that we will be covering in this presentation, let's say that we are not addressing the failure modes of the structure. Rather than this, we are focusing on the operational vulnerability. And this is related to the stoppage modes of the ship, which can be affected by different hazards such as wind, waves, currents, variation of water level, overtopping, etc. Therefore, we'll be addressing the sensitivity of operational vulnerability due to climate change, and this is strongly linked to a concept that is shared between different professions, which is the concept of risk. This concept is understood by politicians, port authorities, port terminals, stevedores, captaincy, etc. From the different definition of risk, Gomez and Molina in 2018 identified a general formulation depending on three interconnected concepts: the probability, the vulnerability, and the consequences. Risk is a useful concept to assess climate change as it allows to evaluate different scenarios, quantifying them, and based on that, planning actions with strategies of adaptation or mitigation. In the present work, we will present a methodology for assessing the operational vulnerability of a port, which applies to different climate change scenarios, allows analyzing the sensitivity of this vulnerability against the different scenarios. This methodology is applied to a case example in the Port of Gijón at the north of Spain. In order to evaluate the vulnerability of port areas, it is necessary to identify which elements are vulnerable, which are the hazards that can affect the infrastructure and operations, and which are the mechanisms that produce the failure, the downtime, or the loss of productivity. In this sense, Puertos del Estado has been investing in monitoring several Metosian parameters such as waves, currents, sea level, or wind for a long time, and little by little this monitoring is being extended from deep water to coastal areas and to port areas. Based on this monitoring, modeling can be developed, and thanks to this amount of information, risk management models can be built in order to support port management and exploitation. Little by little, ports are becoming a living lab with real problems, real challenges that need to be faced. In 2013, Puertos del Estado decided to carry out an interview to most Spanish ports to establish future strategic lines based on a deeper knowledge of the real need of each port and also of the port system as a whole. From these interviews, it can be stated that, as expected, wave-based hazards and wind-based hazards are the ones with a higher concern. But also hazards such as extreme rain were identified as relevant, affecting the operations inside the port. However, the researches on operational vulnerability regarding local high-resolution wind or waves are still limited due to the complexity of the problem and also due to the lack of high-resolution Metosian information until recently. For this study, we have selected mainly the vulnerability due to wave action inside the port. Okay, so we have identified the hazard that we will be studying, but wave action highly differs inside the port. Here we introduce the concept of geoprobability, and it brings together two key aspects of risk management and decision making in ports. First one is the probabilistic nature of the risk, both regarding the hazards and the response of the system, and secondly, the importance of the spatial component in port areas. This component not only has to do with the local effects and how Metosian agents particularly interact with the different port areas, but also with the heterogeneity of uses, typologies, handling means, and ultimately with the vulnerability of each element or system. In 2017, Molina et al. Proposed the concept of areas of operational interest to refer to port spaces with the same functional activity, sharing infrastructural typologies, handling means, land uses, etc., and which are subjected homogeneously by Metoxian agents. The definition of the areas of operational interest offers the opportunity to identify and characterize each subsystem, the specific failure stoppage modes and their interconnection, also to highlight which agents need to be monitored and modeled for being predominant, and also to allow a systematic approach towards risk management, establishing a spatial structure for gathering knowledge and experience. Indeed, for the present case study, this subdivision of port spaces allows the assessment of the vulnerability of operation at the port, as well as the comparison between different climate change scenarios. In this case, we have divided the port into 32 areas of operational interest, attending to an homogeneous wave agitation behavior, and classifying all areas into 4 homogeneous groups for allowing an easier intercomparison with different climate change scenarios, rather than comparing one by one of the areas. 3 different thresholds were assigned to each of the areas, despite being based on the limit operating condition from the Spanish recommendation for maritime works. These thresholds are established here for the sole purpose of providing reference for an intermodal and intramodal comparison between the propagated results from the different climate change scenarios. 3 general circulation models from the CMIP5 were chosen for the cases sampled. They were used in relevant studies such as the AR5, the 5th assessment report of the Intergovernmental Panel of Climate Change, and we selected one of severe wave action at Gijón, another of medium energy, and a low energy one. We also selected 2 concentration scenarios, and in line with other publications such as the already mentioned AR5, spans of 20 years were selected as time horizons using a common criteria of a control scenario, short-term scenario, and long-term scenario. As sea level influences the propagation of waves near shore, it needs to be taken into account. In line with other studies, a mean level is assumed for the calculation of operational descriptors, and sea level rise was considered as a mean value along each time horizon. The mesoscale of the general circulation model is too coarse for considering local effects, which in the case of wave propagation are fundamental regarding wave transformation, non-linear processes derived from local interaction with the bathymetry and contours. The classical methodologies to enhance the resolution of wave trends in coastal areas are statistical downscaling and dynamic downscaling. In the present study, the hybrid methodology suggested by Campos in 2011 is used, as it combines the best of both classical methodologies. First of all, the wind component from each general circulation model are propagated to a deep water location close to Gijón. From the time series simulated at deep water, 300 representative climate states are selected with a maximum dissimilarity algorithm. For each of the selected Metoxian states, which are about 0.5% of all of them, dynamic downscaling simulation is carried out with a warm-up time of 4 days, and once the dynamic downscaling simulation are completed, the whole wave agitation time series at each area of operational interest is reconstructed by means of an interpolation approach with radial basin functions. For the evaluation of the vulnerability, we have proposed a peak over threshold analysis to each of the unique values of an wave agitation time series at each area of operational interest. In this way, if a threshold approach is used, these graphs provide operational information for every agitation value. Having a look at the results of significant wave height at deep water, the first conclusion is the large intermodal variability, more noticeable than the intramodal variability regarding different concentration scenarios and time horizons. This variability is especially evident for the highest values. In general, mean values tend to decrease in future scenarios, whereas maxima trends are more erratic, but in general tend to increase. In the graphs, polar PDFs of wave direction are aimed to illustrate intermodal and intramodal differences, as changes in wave direction are also likely to modify wave agitation inside ports. The results of the propagations up to the areas of operational interest also show a high intermodal variability. Here we are seeing from left to right the mean exceedance events per year for each unique value of wave agitation, the probability of non-exceedance, and the mean duration of the exceedance events. The little graphs with dots represent the specific magnitudes of these variables for the chosen thresholds, in which it is also very noticeable the differences between models. We also see that the intramodal variability is higher for long-term scenarios. In deep waters, there was a reduction in wave height for the values below the upper tail. In this case, the reduction is not so evident up to the point that in some scenarios, wave agitation is increased. See, for example, the results of the most severe general circulation model in short-term scenarios. These are the results for type 1, and there are a lot of similarities with type 2, in which, as expected, the energy is higher. These are the results for type 3, and finally these are the results for type 4, which are the most exposed areas, so the energy is higher, but the same comments that we already did for type 1 are also applicable to the rest of them. So finally, let's sum up the conclusions of these works. We have proposed a general methodology and we applied it to address the operational vulnerability of a port and its sensitivity to climate change, including concepts such as geoprobability by means of the areas of operational interest. The results show that intermodal differences are more significant than intramodal differences. The latter suggests to be cautious in the interpretation of the results, and also the importance, beyond the results themselves, of a systematic and modular methodology to be able to automatically update the results with future models, such as the ones that have been already published from CMIP6. In line with other regional studies applied in the North Atlantic sub-basin, mean significant wave height at deep waters tend to decrease in future scenarios. Maxima trends are more erratic, but in general tend to increase. And despite the general results at deep waters, detailed studies inside ports are needed, as the effects on the operability also depends on the variation of other variables such as wave period or wave direction. Thank you very much for your attention, and I would be glad to at least try to answer any question you may have. Thank you.